Good morning class and welcome to our continuing lectures on climate dynamics, variability and monitoring class. Today we will continue our discussion on some worked out examples based on the equations that we looked at in the last few classes, and then we will further discuss the theory associated with the various climatic variables. So, in the previous class, we discussed that we have the hydrostatic balance equation, which we can write as follows. So, the hydrostatic balance equation we can write this equation as G equals to minus 1 by rho dP dz, okay, where by ideal gas law rho is equals to P by RT. Hence, we get G equals to minus RT by P into dP dz. Okay, so minus R, here R is the gas constant for air, into temperature in kelvins by pressure by the gradient of pressure with altitude. Okay. So, if we let me just change this. So now d of log P can be written as dP by P, correct? So this implies we can write the hydrostatic balance equation as G equals to minus R air into T into d of log P by dz, okay, which implies that dz is equals to minus R air into T by G into d of log P. Let me write this properly. So this implies dz equals to minus R air into T by G into d of log P. Okay. So this is an alternative form of the hydrostatic balance relation. So alternative form of hydrostatic balance relation. Okay. So now, what are we trying to do with this? So the idea here is, it is not necessarily the case that temperature is constant. We have used in the previous case, remember H basically is the scale height. So this expression we have written as H. Okay. So in general, we defined scale height H as R air into T by G, correct? However, if the temperature is a function of Z as is the case in actual conditions, then using the scale height relationship may not be quite accurate. Alright. So what we will do instead in this case, so for a more generalized case, T is a function of Z. Okay. So remember in this context that if we plot Z and T, what we were getting before is something like this. Correct? Approximately. So this is kind of the troposphere. This region is the stratosphere. And beyond this is your mesosphere and the exosphere. Okay. And each of these regions, the change of temperature with gradient is more or less linear. So let us consider that for the troposphere, we have the fall off gradient, or it's often also called the lapse rate, gamma as minus dt dz for the troposphere. Okay. And this gamma, which is the slope of the change in temperature with altitude, can be considered constant in the troposphere. We will have a different and a negative lapse rate in the stratosphere. Again, the lapse rate will change. So for each of these zones of the atmosphere, we will have different lapse rate values. Okay. But let us consider our case only for the troposphere, which is approximately varied from 0 to 12 kilometers of the atmosphere. So in this case, we have dt is equals to minus gamma dz, where gamma is a constant positive value for the troposphere. Okay. Now, if you go back, we have expressed dz in this type of formulation. Okay. So we can replace dz in this expression by this expression here. So if we do that, so this implies dt equals to minus gamma into R air into T by G into D of log P. P is the pressure of the atmosphere. Okay. Now we can take this temperature here. So we get dt by T is equals to minus gamma R air by G into D log T. But dt by T itself is D log T. So we get D of log T equals to just one correction, dz is minus here. here you have minus, so minus minus will cancel, so you won't have this minus sign here. Okay, so this is a positive term. Sorry for the mistake. So we get d log t equals to gamma into r air by g d log p. All right. So this is the expression we will get assuming a constant lapse rate for temperature in the troposphere. Okay. So now we integrate from z equals to 0 to z equals to say z1, some altitude z1 which is below the troposphere, where z1 is within the troposphere. Okay. Now at z equals to 0, we set P equals to PS, the pressure at sea level, and T equals to TS, the surface temperature of air. Okay. And at z equals to z1, we set P equals to P at z1 and T equals to T at z1. All right. So if we put this and do an integration here within the limits, we will have log of T at z1 by Ts equals to gamma gas constant for air by G log of P at z1 by PS. All right. So then we can take out the logarithm and get, hence for any altitude z1 within the troposphere, we have T, the temperature at the altitude z1 by Ts equals to pressure at altitude z1 by Ps to the power gamma R air by G. All right. So this is an important expression here. Now the next question is, can we simplify this further? All right. So remember that gamma is equals to minus dt dz. Okay. This implies dt equals to minus gamma dz. Since gamma is a constant, we can integrate this term as well from z equals to 0 to z equals to z1. So integrating from z equals to 0, which is at sea level, and z equals to z1, we get T of z1 minus T of s equals to minus gamma z1 minus 0. All right, which implies temperature at z1 equals to temperature at the sea level minus gamma into z1. this expression here. Okay. So we have these expressions. Now temperature at Z1 is temperature at sea level minus gamma Z1. So we can put that expression here and get, so Ts minus gamma Z1 by Ts equals to pressure at Z1 by the sea level pressure to the power gamma R air by G. Okay. Implies 1 minus gamma Z1 by Ts. So we are just taking this common, equals to Pz1 by Ps into gamma R air by G, which implies that pressure at Z1 is equals to the sea level pressure into 1 minus gamma Z1 by Ts to the power G by gamma into R air. Okay. So this is the final expression that we are getting. Alright, so this is the final expression. So we can compare this expression with the expression where we kept the temperature as the mass averaged mean temperature and plotted the pressure profile that way. Okay. So remember that for our atmosphere, the mean lapse rate, so gamma mean is equals to 6.5 kelvins per kilometer in the troposphere. Okay. All right. And Ts is approximately 15 degrees centigrade or 288 kelvins, and PS is 101,325 pascals. Okay. And RAR is 0.287 kilojoules per kg Kelvin for air. So with these expressions, we can determine the variation of pressure with altitude within the troposphere. Alright. And we can compare that with the more simplified case where we would put the temperature to be a constant mean average temperature value and got an average scale height. Okay. So we can compare these two and check what are the differences. So this is all of the worked out example for now. So let us go forward and discuss a little bit on the next part of our discussion. So here we have looked at the pressure and we have looked at how the pressure fall off can be expressed either for the case of an average temperature case or a temperature that is varying linearly with altitude. Okay. And we saw a few examples of using these two expressions. Alright. Now, in atmospheric sciences, several units of pressure are popularly used interchangeably. So, it is good to have a table where all the pressure units are related with respect to each other. So, the SI unit of pressure, which is the standard international unit of pressure, is 1 Pascal, which is 1 Newton of force over 1 meter square of area. Okay, it is also called 1 PA. Okay. Now, 1 hectopascal is equal to 100 pascals. Okay, so when you are looking at a hectopascal as a unit, it is equals to 100 pascals. Similarly, an alternative unit is 1 millibar, which is also 100 pascals. So, 1 hectopascal and 1 millibar are basically the same units expressed in terms of different descriptions. 1 kilopascals is of course 1000 pascals. 1 bar is also a unit of very popular unit of pressure, which is 10 to the power 5 pascals. So, which is why millibar, which is 10 to the power minus 3 bars, is 100 pascals. So, 1 kilopascal is 10 to the power 3 pascals, 1 bar is 10 to the power 5 pascals. 1 atmosphere is close to 1 bar, which is equals to 101,325 pascals. So, this becomes 1.01325 bars or 101.325 kilopascals. Okay. Then you have one of the highest units of pressure, 1 megapascals, which is equal to 10 to the power 6 pascals. So, these are all basically units in terms of pascals except the 1 atmosphere unit, which is slightly different from units of orders of 10. Okay. Then you have the English unit of pressure, which is 1 psi, which is still common in many engineering disciplines. It is pound force per square inch of area, which is equal to 6894.8 pascals. Okay. Another popular unit is 1 torr, which is equals to 1 millimeter of mercury column. This is used in common places in the barometric pressure readings. So, this is basically 1 atmosphere is approximately 76 millimeters of mercury column. So, 1 torr is 1 by 760 of that. So, it is 76 centimeters, so 760 millimeters. So, 1 atmosphere is basically 760 torrs. So, 1 torr is 1 atmosphere by 760, which is 133.32 pascals. Okay. So, these are the common units of pressure that we will discuss as we go along in the course. Okay. So, this kind of completes our initial discussion on pressure and the vertical variation of pressure, how to solve for it. Okay. In the next class, we will discuss atmospheric humidity, which is another very important variable when it comes to climatology as well as weather, because when air is hot and humid, you will have convection currents that leads to cloud formation, and as well as the fact that water vapor is a strong greenhouse gas. The extent of water vapor carrying capacity of air is also a very important criteria determining the extent of anthropogenic global warming. So, we will discuss that briefly here, with further discussions postponed to later in the class. So, today I am stopping here. Thank you for listening and see you in the next class.